Oh, Okay, welcome back, friends. In the last session, we have started our discussion on electromagnetic fields. Okay, good evening. So, in the last session, we have discussed what is called a vector calculus operators. What are the vector calculus operators? Divergence, curl, gradient, Laplacian operator. So, we have given the interpretation as well, isn't it? For each and every operator. These are divergence. These are curl. And then we also seen the gradient operator. It is a both divergence and curl. Here it is a gradient operator. It is a Laplacian operator. So all these are differential. What are the operators we have discussed so far? Divergence, curl, gradient, Laplacian operator. All these are operators are called differential operators, or they are also called point operators. Okay, so they are defined at some particular point. They are defined at some particular point. I want to extend this concept to the any arbitrary closed surface. Any arbitrary surface. What is the meaning of divergence? If you recall, net flow from the small piece of a box. What is the meaning of divergence? Net flow from the small piece of a box. Just a minute. The divergence is net flow from the small piece of a box. Divergence is a net flow from the small piece of a box. And what about the curl? Net rotation observed on the small piece of area. And what about the gradient? The magnitude of the gradient is maximum rate of change of scalar quantity in the three-dimensional space. And the direction of the gradient is in the normal direction. Clear? Now, today's session, we're going to start with what is called integrals. We're going to see the same things for any arbitrary surface. Suppose if I want to find out what is the net flow from the closed surface, or what is the net rotation on the area. Fine. So we're going to see the cumulative effects of this divergence, which leads to what is called integrals. Fine. So let us start with today's discussion with the integrals. There are three types of integrals here. One is a line integral, other one is a surface integral, other one is a volume integral. And there exists a relation among them, which is called a Stokes theorem and then a divergence theorem. Clear? Fine. So let us have discussion over them. Now let us start with what is called integrals here. Before going into the line integral, you should know some basics here. I'll call it as a basic. Basic number 1. We're going to discuss what is called a vector resolving technique. Vector resolving technique. What is the vector resolving technique? Suppose if you have got a vector like this. Here it is x-axis, here it is y-axis. There is a vector field F here. It is making some angle theta here. What is the component of vector f along the x-axis? I want to find out the shadow of f over the x. Let us make some vector like this here. What is the shadow of, or other words, what is the equivalent of the vector over the x? You can make a triangle here. What is this? This is adjacent side. Adjacent by hypotenuse is a cos theta. So here it is f cos theta. And what about this length? This length is equal to this length. Yes. So what is this one? Here it is f sin theta. So wherever it is, just easy to remember, wherever it is making angle, this is cos theta. Other side it is sin theta. Yes. So wherever it is making angle, it is cos theta. Other side it is sin theta. Clear? Yes. Now basic number 2. There is a dot product here. I want to multiply the two vectors. There is a dot product. Yes. So there is a vector here like this. And there is a vector here like this. Here is a vector f1. Here it is a vector f2. I want to multiply these two things. Let us say they are making alpha with each other. So what is the component of f over f2? f2 over f1. Here it is f2 cos alpha. They are making alpha with each other. What is the vector of f1 over f2? What is the shadow of f1 over f2? You can call it as like that. Here it is f1 cos alpha. Clear? Yes. So what is the meaning of I want to multiply the two vectors? The direct product is not possible. So what I'll do, I'll find out the component of one vector over other vector. I'll find out the component of one vector over other vector, or component of this vector over this vector, and I'll multiply them, which is called a dot product. F1 F1 dot F2 is equal to F1 into F2 cos alpha, or F2 into F1 cos alpha. So these are the two techniques. Those are the two basics you should know in understanding what is called a line integral. Let me turn the page here. So let us try to understand what is the concept of line integral. Okay. Let us perform the line integral. What is the meaning of line integral? Let us consider the vector field F. Here it is a vector field F. Okay. When I draw a single arrow, it must indicate, it will indicate what is called a field. It is not a simple vector. Field means what? It is present in the region like this, like this, like this, like this, like this, like this, and so on. Okay, it is present in the region. There is a vector field like this, like this, like this, like this, like this, like this. I want to perform what is called a line integral. What is the meaning of line integral? Observe here carefully. I want to integrate it from initial point to final point. So the vector field is present here like this, here like this, here like this. So I want to multiply here the vector field into contour or a line. Yes, that is what I wanted to do in the line integral. This is initial point. This one is a final point. This is the initial point and that is the final point. I want to perform vector field into length, and this is the direction of the, this is the direction. The direction of the contour is from initial to final point. So I want to multiply a vector field into length. I want to multiply vector field into length. Is it possible directly? No. They are making some angle here. They are making some angle here. They are making some angle here. Yes, I will going to make this one into a small pieces. I will going to make the contour into small pieces. Here it is DL1. Here it is DL2. Here it is DL3. Here it is DL4. Up to here it is DLN. I am making the contour into pieces. Each piece is looking like a straight line. In that small piece, I will perform the dot product. Step number 1. So I will perform F dot DL. I want to multiply vector field into contour. So the direct product is not possible. I am making the contour into pieces. Each piece is looking like a straight line. So in that small piece, I will perform the dot product. And I will add all such dot products here. Here it is F dot DL1 plus F dot DL2 plus F dot DL3. So on up to F dot DLN. This is called line integral. This is initial point. This is the final point. F dot DL. This is called line integral, or it is also called contour integral, or it is also called rotation or circulation. Line integral, contour integral, rotation or circulation. Number 3. Okay. So what this is called? This is called line integral. Or it is also called contour integral. or it is also called rotation or circulation. These are the different names given. Clear? Yes. Now let us proceed further. So where I have started, I'll come back to the same point. This is called what? Closed line integral. This is called what? Closed line integral. If I perform the integration over this, then it is called closed line integral. Closed line integral or closed contour integral or net rotation or net circulation. Here it is. Closed line integral. Closed contour integral. Or net rotation. Or net circulation. Okay, I am coming back to the same point where I have started. Then I'll ask a very basic question. What would be the value of this closed line integral value? I want answer from your side. So I'm coming from the same point. What is the meaning of dot product? Dot product I've already explained here. Zero is a wrong answer. Zero is a wrong answer. It need not be zero. It need not be zero. Why to do line integral? I'm explaining the line integral. I'll give the application. This value need not be zero. Okay. So that only is zero. That is only zero for the conservative fields. We'll talk about that one later. Okay. That depends on the nature of the vector field. If the vector field curl is zero, then its closed line integral is always zero. We'll talk about that point later. Okay. Then what is the essence of the line integral here? We are performing vector field into length. The direct product is not possible. That is the reason why we are making the contour into pieces, n number of pieces. For every piece, we are performing the dot product. That means we are finding the component of vector over that small piece of a length, and you are adding all such points right from initial to final point. Okay. So what is the essence of the line integral? To put in a simple words, the essence of the line integral is to multiply the vector field into contour. Vector field into contour. Clear? Yes. Let me turn the page here. Vector field into contour. So the only application of this line integral is the evaluation of work done. Let us consider if it is a force field. force into distance or displacement. Yes. So what you're going to get? You're going to get a work done. Fine. So let us make some observations here. The closed line integral. Closed line integral need not be zero always. Closed line integral need not be zero always. Point number 2. What is the second point here? What is the application of the line integral? What is the application? The only application is evaluation of work done. Evaluation of work done. Okay. So later we're going to find out what is called electrostatic potential. We're going to find out work done there. So there is a, there we're going to use this one. And one more point here. One more observation. If it is a closed contour, if it is an open contour, if it is an open contour, right from initial to final point, is it having any volume, any surface? If it is an open contour, observe here carefully. If it is an open contour, it has got no area. But once it is a closed contour, inside the closed contour, there is an area. What kind of area? Closed area. I mean, open surface, isn't it? Open contour has got no surface, but closed contour is having a surface inside that. Isn't it? So what you have noticed here? Closed contour encloses open surface of infinite shapes. Isn't it? Suppose if you are having, for example, suppose if you are having some ring like this. This is a contour C. Inside this one, there is an area. Let me call it as a S0. So the closed contour is encloses open surface. It can enclose the other open surface also. It can have other shape also. For example, this is a cup here. This is a cup here. This is a closed contour. It is having a surface like this, like a bulged surface. Is it open surface or closed surface? This is an open surface. With the same contour, suppose if I suppress this cup, what you will going to get? You will going to get a flat surface. That is what I have shown. So with the same contour, I can have, you see, for the same contour, I can have a flat surface, I can have a bulged surface. I can have a surface like this. I'll call it as a S1 surface. With the same contour, I can have a surface like this. With the same contour, I can have a surface like this. S3 and so on. So with the same contour, I can have a flat surface. I can have a surface like this. I can have a surface like this. I can have a different surface, something like a, with the same contour, I can have a disc. I can have something like a skull cap. I can have something like a Himachal Pradesh cap. This is a Himachal Pradesh cap. Or I can have something like a birthday cap, isn't it? With the same contour. So what you can say here, closed contour encloses open surfaces, isn't it? Closed contour encloses open surfaces of infinite shapes, isn't it? So with the same contour, I can have a different surfaces. That is a extremely important observation. What is the contour? Line is called contour. Yes. So what is the note here? Note. Closed contour encloses open surface of infinite shapes. Here it is in brackets. C. Here it is S0, S1, S2, S3, so on. Clear? Closed contour encloses open surfaces of infinite shapes. S0, S1, S2, S3, so on. Clear? Let me turn the page here. So this is all about the what is called a line integral. What is the application of the line integral? Evaluation of work done. Let me turn the page. We need to go to the what is called a surface integral. But to go to before going into the surface integral, you should know some basics. Basic number 3 I will call. Area direction. Just a minute. Yes. What is the area direction? Suppose if you consider some area like this, is there any direction for that one? No. If you consider some area like this, some piece of a paper, if you consider some area like this, let me take some area, piece of a paper. Suppose if you consider some area like this, is there any direction for this one? No. There is no direction for the area, strictly speaking. But I want to use this one in the mathematics. I want to use this one in the mathematics. So we're going to define the normal direction. Which direction? According to mathematics, the area direction is a normal direction. Okay. Fine. So this is the open surface, isn't it? This is the open surface. For the open surface, the normal direction is not unique. It can be this side or even this side also. But for the closed surface, something like a bottle, it is always considered outwards. Okay. So now let me write down here what it is. The area direction. What it is? The area direction is normal to its own surface. The area direction is normal to its own surface. Okay, next point. For the open surface, normal direction is not uniquely defined, but for the closed surface it is considered always outwards. So for the open surface, normal direction can be this side as well as this side. But for the closed surface, something like in balloon, it is considered always outwards. Okay. So for the open surface, it is not uniquely defined. It can be this side or this side. But for the closed surface, it is considered always outwards. Clear? So with this background, let us try to understand what is called a surface integral. I'm going to turn the page here. Surface integral. What is this surface integral? Let us consider the vector field F. It is a vector field. When I draw a single arrow, you must understand that it is a vector field. It is present in the region like this, like this, like this, like this, like this, like this, like this. So what I'll do here, I'll place some surface here. Okay. So I'll going to place some surface here like this. So the vector fields are entering from here and leaving from here. Vector fields are entering from here and leaving from here. Vector fields are entering from here and leaving from here. Leaving from here. I want to find out what kind of surface I have considered. This is the open surface. Okay. So I want to find out what is the total vector field crossing this surface. I want to find out what is the total vector field crossing this surface. Clear? So what I will do, I'll consider a small piece of area here. dA. I'll consider the normal direction in this way. Okay. Why I have considered the normal direction in this way? Just to I wanted to show you. Because it is the open surface. Normal can be this side as well as the other side also. Normal can be other side also. Isn't it? Just I wanted you show this one. Okay, fine. Now observe here carefully, step by step. Step number 1. There is an area direction. What is the area direction? I want to find what I want to do here in the surface integral. I want to find out what is the total vector field crossing this surface. So what is the amount of vector field crossing this surface? Step number 1. Actually, there is no direction for the area. but I'll give the direction to the area. Which direction is that? Normal direction. So then it will become a vector. Step number 2. I'll find out what is the vector field crossing this small piece of area. Okay. So here it is F dot dA. Number 3. I'll find out what is the total vector field crossing this surface. Okay. So I'm going to add up this one in this way as well as in this way. That is called a surface integral, isn't it? So surface integral of F dot dA. This is called surface integral, or it is also called flow, or it is also called flux. What this is called? This is called surface integral. Or it is also called flow, or it is also called flux. Flux need not be electric flux or magnetic flux. The amount of vector field crossing through the given surface is called flux. Okay. So let us consider step number 4. Suppose instead of the open surface, if I would have brought some closed surface, something like a balloon. If I would have brought some balloon, something like this. So if I brought some balloon, there will be an inflow as well as outflow. Yes. So then it is represented with the closed surface here. You should remember all this terminology. Closed surface integral of F dot dA. This is called closed surface integral. Or it is also called net flow. Or it is also called net flux. Clear? Yes. Net flow or net flux. Clear? Okay. Suppose if you are having an open surface, then there is no volume. But once there is a closed surface, there is a volume inside that. Yes. So here it is. Closed surface. What it is? Closed surface encloses volume. So what you can do by using what is called a surface integral? By using surface integral, you can find out amount of vector field crossing the given surface. That is called a flux. Yes. The amount of vector field crossing the given surface is called flux. So what is the application of this one? Evaluation of flux. Evaluation of flux. Clear? Yes. Closed surface encloses volume. What is a surface integral? What you can do by using the surface integral, you can evaluate what is called a flux. So this is all about the surface integral. Clear? Step by step, clear. Next, last one is a volume integral. Next one is a volume integral, beta. In the volume integral, we'll use what is called a scalar field. So what we're going to use? We're going to use what is called a scalar field. Let the scalar field is a F. Okay. So now the scalar field, then one can ask why we are not taking the vector field. Vector field, we do not have any application. Only there is application for the scalar field. Okay. So we are discussing so here we are discussing what is called a scalar field. Vector field has got no application. Okay. Now let us consider the closed surface like this. What is this one? It is a closed surface. It is not a flat one like this. It is a closed one, something like a mango. Okay. Let me put some dots here. Why I am putting dots here? To create the field that it is a three-dimensional one. Okay. And inside this one, it is filled with the scalar field. Something like a liquid which is not moving. Okay. Now let us consider the volume here. And there is a scalar field F here. I want to find out what is the total scalar field inside the volume. That you can do it by what is called a volume integral. Step number 1. What I will do, I will find out what is a scalar field inside a small piece of a box. F into dV. And I will going to add all such boxes. Number 2. In the 3 dimension. Volume integral of F into dV. This is called volume integral. This is called volume integral. So what you can do, what is the application here? You can find out, you can evaluate the total scalar field inside the volume by using the volume integral. Yes. So what is the application of this one? Application is evaluation of total scalar field. So this is all about what is called a volume integral. Let me go back. What is a surface integral? It is the evolution of flux. What is the meaning of flux? The amount of vector field crossing the given surface is called flux. Let me go back. What is the application of the integration? Line integral is evaluation of work done. Let us take the questions here. We're going to take one question on the line integral, surface integral, and then volume integral. Okay. Just a minute. Okay. Let us take the questions here. Here is a question. The given vector field F is equal to yx cap plus xy cap. Given a vector field F is equal to yx cap plus xy cap. Evaluate integration from point P1 1 comma 1 comma minus 1 to 1 comma 1 comma minus 1 to point P2 2 comma 4 comma minus 1 along the parabola y is equal to x square. Yes, how do you do this one? Any answers from here? Yes, how do you approach for this one? Yes. See here, now let me explain this question here. Given a vector like this, f is equal to yx cap plus xy cap. Evaluate the integration from point P1 to point P2, 2 comma along the parabola y is equal to x square. Let us consider the vector field F. When I draw a single arrow, you must understand that in that region there is a vector field. Okay. I want to integrate it from what point beta? Point P1 to point P2 along the parabola y is equal to x square. You no need to write any running notes. Whatever, all the required things I have written. Amount of vector field crossing the given surface is called flux. All the required things I have written. No need to write any running notes. Just remember these punchlines here. Evaluation of work done. All the necessary things I am writing here. Okay, come back to this question. So here you need to perform like this. This is a question. Okay, you need to perform the integration here. The integration I will call it as a I. The I integration is from point P1 to P2 F dot dl. So then what is this differential length dl? What is this differential length dl? Let us consider the coordinate system. I haven't discussed the coordinate system, but still you can answer this question. Here it is the x-axis, here it is the y-axis, here it is the z-axis. I want to move a small distance from 1, 1, 1 to 2, 2, 2. A point 1, 1, 1 to 2, 2, 2. So if I move from a point 1, 1, 1 to 2, 2, 2, how much distance I have moved along the x-axis? 1 meter. Along the y-axis, 1 meter. Along the z-axis, z meter. Okay, suppose if I consider a small piece of a length here. Now let us consider a small point here. What is the point here? X, y, z. And I will consider this point as x plus delta x, y plus delta y, z plus dz. And what is the length of a line we have considered here? The length of a line is dl. Clear? So how much distance I have moved along the x-axis? Along the x-axis, I have moved a distance of dx. Along the y-axis, what is the distance I have moved? By dy. Along the z-axis, dz. Clear? So this is the distance, is the moment along the x-axis, y-axis, and then z-axis. Clear? Okay. Now here, see here. So how can you write the differential length dl here? The differential length dl can be written as dl is equal to dx x cap dx x cap dx x cap plus dy y cap plus dz z cap. Yes, so here it is a differential length. Here it is a differential length you can call. This is. This you need to remember for the line integral. This will going to help us for performing what is called a line integral. Differential length. Clear? Okay, fine. Let me turn the page here. So once you have got a differential length, just to substitute there. Yes, one of your friend has given answer also. Let me turn the page here. So what happens to this one beta? So the integral I is equal to line integral of f dot dl beta, isn't it? What is f? Yx cap plus xy cap dot product with dx x cap plus dy y cap plus dz z cap. Yes. So here it is. Here it is x cap. Here it is x cap. Here it is y cap. Here it is y cap. So after performing the dot product, what you will be left with? You will be left with y dx plus x dy. So here it is given that there is a relation between x and y. Make a use of that. So here it is y is equal to x square. So you can write dy is equal to 2x into dx. Convert this one into single variable, either x or y, your wish. So here it is x square into dx plus x into 2x into dx. So I is equal to, here it is 3x square into dx. So integral I is equal to 3x cube by 3 into dx. Sorry. What is the integral value beta? 3x cube by 3. Limits are, what are the limits here? What are the limits here? The limits are, x limits are from 1 to 2. Clear? Upper limit minus lower limit. 2 cube minus 1 cube, which is equal to 7. 7 is the answer. So while solving this question, I have also given one thing, differential length. Okay, let me turn the page. We'll have one more question. This is all about the line integral. Let us have one more question. How we got f? F is given in the question. It is provided in the question itself. Let us have one more question here. The vector field in certain region is described as f is equal to xy x cap plus yz y cap plus zx z cap. The amount of vector field crossing the plane x is equal to 4 meters and bounded by the limits and bounded by the limits y 0 to 2, comma z 0 to 4 meters is. So what should I do in this question? Come on, speak out. I want answers from your side. The vector field in certain region is described as, it can be anything. These is a vector field. The amount of vector field crossing the plane x is equal to 4 meters, bounded by the limits x comma y is ranging from 0 to 2 comma z is ranging from 0 to 4 is. Yes. So what I need to do here? What kind of integration I should perform? Come on, speak out. What kind of integration? Flux, very good. Surface integral, very good. Is it an open surface integral or closed surface integral? Is it an open surface integral? Is it an open surface integral or closed surface integral? What kind of integration I should perform? Just a minute. Yes. So what should I do? I should perform what is called open surface integral. Double integral. Okay. Why? It is an open surface integral. How can I notice that one? See here in the question, it is saying that crossing means what? It is something related to the flow or a flux. In the question, it is mentioned that it is a plane. Plane means something like this. It is an open surface integral, isn't it? Fine. It is a open surface integral. It is a plane. And you can also notice from the units here, limits here. What are the limits? X is equal to 4 meters. And the two variables, two coordinates are changing here. If two coordinates are changing, it is a two-dimensional. then it is a surface. If three coordinates are changing, it is a three-dimensional, then it is a volume. If two coordinates are changing, it is a two-dimensional, it is surface. If three coordinates are changing, it is three-dimensional, then it is a volume. If only one coordinate is changing, then it is a line. If no coordinates are changing, then it is a point. That is a simple observation. Clear? Yes. Now, what I will do here, let us try to draw something here. Let us draw some coordinate system here so that I'll get the thing here is you need to find out what is called a flow or flux. It is represented with the symbol psi. Surface integral of, we need to find out f dot dA. Clear? Here it is x-axis. Here it is y-axis. Here it is z-axis. X is equal to 4 meters here. X is equal to 4 meters. 1, 2, 3, 4. Y is equal to 2. 1, 2. Z is equal to 4. 1, 2, 3, 4. Let us make some box out of this one for the 3D visualization. But what is the plane we are interested? We are interested in this plane. Okay. Yes. So he's asking what is in this region, there is a vector field F. He's asking what is the amount of vector field crossing through this surface. But what is the surface? Here it is, what is the area of this one, beta? If you want to write the differential area. What happens to the differential area here? Here it is dy. Here it is dz. The area direction is like this. Here it is x cap. Then what happens to the differential area? Small piece of area can be written. Differential area dA. Here it is dy into dz into plus or minus x cap. Isn't it? Dy into dz into plus or minus x cap. Why? Because normal can be this side, because it is the open surface, or other side. Now what I want to do here, that is how you, by drawing the figure, you need to decide the differential area. But there is a, I want to develop something here so that without any diagram, you can directly decide. Okay. So without any diagram, how can you decide? Here you have considered what is called, here you have considered what is called, here you have considered YZ plane. In the Y, if you consider YZ plane, direction will be in the X. Similarly, if you consider XY plane, direction will be in the Z. Okay, with that logic, how I can write? So differential area, standard form can be written like this. dA is equal to dx into dy into z cap plus plus or minus z according to the question you need to react. If you consider yz plane beta, here it is dy into dz into x cap plus dz into dx into y cap. Here it is differential area. So if the you need to you can easily remember this one, isn't it? Then what is the required differential area can be obtained? Here you can notice that x is equal to 4 meters, isn't it? You can just substitute there. Here x is equal to 4 meters. If x is equal to 4 meter, what is dx? Dx is equal to 0. That means what are the terms will go 0? This term will go 0 and this term will go 0. What remains is the this term. Yes. So that we already seen. So this implies that dA is equal to dy into dz into x cap. Okay. Now let us try to find out the flow or a flux which is represented with the symbol psi. Now come back to the integration here. Here it is surface integral of f dA. What is f? xy x cap plus yz y cap plus zx z cap dot product with dy dz x cap. So after dot performing the dot product, what will remain? This term will remain. Clear? Yes. So what happens to the psi? Psi is equal to surface integral of x into dy into dz. Here on this plane, x is constant, isn't it? You can bring that x outside. So psi is equal to x is a 4 value. So here it is y into dy into dz. Separate out the variables. 4 into y into dy into dz. So here it is 4 into y square by 2. What is the y range? Y range is from 0 to 2. Here it is z. Z range is from 0 to 4. Upper limit minus lower limit. 2 into 2 square into 4. Here it is 32. Units is the answer. Clear? Fine. Now let us have one more question beta. This is on the surface integral. Let me turn the page. We'll have one more question. One more question on the volume integral. The volume charge density in certain region is given by 2x y square z nano coulomb per meter cube. Find total charge enclosed by the box defined by The following limits is limits are given like this. X is ranging from 0 to 2 meters. Y is ranging from 0 to 2 meters. Z is ranging from 0 to 4 meters. Yes, what should I do here? It is clearly mentioned. This is a volume charge density. We haven't discussed about the charge distribution so far, isn't it? Different types of charge distributions we haven't discussed. But still you can answer this question. Yes. So what is the charge density charged here? 2x y square z nano coulomb per meter cube. Find the total charge enclosed by the box and defined by the limits. Yes. Let me turn the page here. Here it is the x-axis, here it is the y-axis, here it is the z-axis. What is the box? He is asking us to find out what is called a total charge, isn't it? Solution. We haven't discussed about the types of charge distributions. There will be a line charge, surface charge, volume charge. We'll discuss later. But still, we can answer this question. What is the total charge Q? Is equal to, here it is, volume charge into dV. Yes. So here, what is the units? This one here it is nano coulomb per meter cube. Multiplied with the meter cube, you are going to get nano coulombs. So here, what is given? Rho v. Volume charge is represented with a rho v, which is 2x y square z nano coulomb per meter cube. Clear? Yes. So what is the box here? X is ranging from 0 to 2. 1, 2. Let me draw some bigger box. 1, 2. Y is ranging from 0 to 2. 1, 2. Z is ranging from 0 to 4. 1, 2, 3, 4. Let us make some box out of this. Clear? Yes. And in this region, it is filled with a charge. Everywhere there is a charge. Charge is characterized as a volume charge, rho v. Units are nano coulomb per meter cube. Here we want to find out charge inside this box. So I'll consider the small piece of a box here. What is the volume of this box? Here this is along the z axis. So what is this length? Here it is dz. This is along the x axis. What is this length? Here it is dx. Clear? This is along the y axis. What is this length? dy. So what happens to the differential volume dv? dv is equal to dx into dy into dz. Clear? So what happens to the total charge? Speak out. So here it is. You need to remember this one as a formula. This is differential volume. What it is, beta? Differential volume. Okay, let me go back. So just to substitute there here. So what is the total charge? Total charge is equal to volume integral of 2x y square z into dx into dy into dz. Separate out the variables. Here it is 2 into x into dx, y square into dy, z into dz, 2 into x cube by x square by 2. What are the limits? The limits are from 0 to 2. Here it is y cube by 3. Limits are from 0 to 2. Here it is z square by 2. Limits are from 0 to 4. Upper limit minus lower limit. So how much is the total charge? Here it is 2 square, 2 cube by 3, 4 square by 2. 16 into 16 divided by 3. How much is the total charge? I'll complete here itself. Yes, how much is that? Divided by 3. 85.33 nanocoulombs is the answer. Clear? Yes. So that is how you need to proceed. Now let us proceed further. Now, while doing this one, we have observed one thing here. What is that? Here is a differential volume, isn't it? You need to remember that. Here it is a differential area. You need to remember it. And here is a differential length. You need to remember this. Clear? Yes? Fine. Now let us proceed further here. So when we are discussing the line integral, we have noticed one observation. The line integral here, observe carefully. If it is an open contour, it has got no surface. But once it is a closed contour has a surface inside that. Isn't it? Closed contour is having a surface. What kind of surfaces? Closed contour have open surfaces of infinite shapes. Okay, so there is a possibility in relating the closed line integral with the what is called a surface integral. That we're going to see with the help of what is called a Stokes theorem. What is the other observation we have made? There is a closed surface here. Here it is an open surface. Open surface has got no volume, but once it is a closed, inside the closed surface there is a volume. So closed surface encloses volume. Clear? Yes. Observe here carefully. So we're going to see what is called a Stokes theorem and then a divergence theorem. Let me start with what is called a Stokes theorem, beta. Yes. So let us start with what is called a Stokes theorem. This Stokes theorem is taken from your Cartesian, from your vector calculus. Stokes theorem and then divergence theorem. Okay. So what does this Stokes theorem will do? Stokes theorem will relate closed line integral. Closed line integral with the open surface integral. Okay. So whenever you are dealing with the Stokes theorem, you need to follow one note. Let me give that note. Note here. In general, normal direction for open surface is not uniquely defined. Is not in general. In general, normal direction for open surface is not uniquely defined. That we also know, isn't it? Suppose if you take the open surface like this, what is the normal direction? Normal direction may be this side or this side. But while using the Stokes theorem, but while relating the closed line integral with the open surface integral using Stokes theorem, it can be defined uniquely with the help of right hand thumb rule. What does that mean? But while relating closed line integral, but while relating closed line integral with open surface integral, open surface integral using Stokes theorem, it can be defined uniquely with the help of right hand rule. With the help of right hand rule. What does that mean? Let me turn the next page. We'll go to the next page. See here, let us consider the vector calculus. Let us consider the vector field here. Let us consider the vector field F. Okay. Yes. Let us consider the closed loop here like this. Okay. So what we're going to do here, we're going to relate the closed line integral with the open surface integral. Clear, beta? Yes. So this closed line integral I call closed contour C. It is having a surface inside that. It can have a flat surface or it can have a bulged surface. It can have any surface. Clear? Yes. So I'll consider the contour direction in this way. contour direction in this way. If I consider contour direction in this way, I need to use my right hand thumb rule. If I put my fingers in the direction of loop, my thumb will going to show the direction of normal. Yes. So this is the contour direction I have considered. So for this case, what is the normal direction, beta? Here it is DA. Yes. So if I put like this, so the thumb is like this. In cap. Suppose if the loop direction is in this way, I need to put my fingers like this. If it is like this, if the loop direction is in this way, I need to put my fingers like this. My thumb will go inside, isn't it? So that is what this note is saying. What is this note I have written? In general, normal direction for the open surface is not uniquely defined. Suppose if you consider the open surface like this, the normal direction can be this side or this side. But when you are dealing with the Stokes theorem, what you are doing in the Stokes theorem, closed line integral is related to open surface integral when you are using the Stokes theorem. When you are using the Stokes theorem, what happens? Closed line integral is you can use your right hand thumb rule. You need to put your fingers in the direction of loop. Your thumb will going to point in the direction of normal. Yes, so this is a precaution need to be taken, beta. So what is the Stokes theorem then? The Stokes theorem here is closed line integral of, let us say it is having a surface S. It is enclosing the surface S. So the closed line integral of FDL is equal to surface integral of del cross F dot dA. This is a Stokes theorem. Okay. So whenever you want to find out what is called a closed line integral, that can be easily done by using this one. Clear? Yes. So this is over the contour C, and this is performed, the surface integral is performed over the surface S. Over the surface S. Clear? Now let us take something, let me define this one completely. Excuse. Let me define this one completely. Remember, it is also valid over the all the surfaces. Let me turn the page here. Let me call it as an extension. It is not actually extension. Complete definition. Suppose if you have got a contour like this. Contour is C. Here it is C. So it can have a flat surface like this. Yes, not. It can have a surface like this S1 with the same contour. I can have surface, different surfaces. Infinite shapes are possible with the same contour. S2. S3. S4, so on. So the Stokes theorem is valid over all the surfaces. Yes, what does that mean? Suppose if you want to perform a closed line integral F dot dl, which is equal to surface integral of del cross f dot dA. Yes. So here it is C, here it is S naught, which is also equal to over the del cross f dot dA, which is also equal to del cross f dot dA, and so on. That means which is also true over the surface S1, over the surface S2, and so on. So this is a complete definition of the Stokes theorem. Hope you have got this one. Clear? Fine. Let us have what is called a divergence theorem. After that, we'll go to the questions. Hope you have got this one. Let me turn the board here. Let us take what is called a divergence theorem better. What is this divergence theorem? What does the divergence theorem will do? Divergence theorem will relate the closed line integral with the closed surface integral with the volume integral. What it is? Closed surface integral with the volume integral. Clear? Yes. Now observe here carefully. So here there is no headache of deciding the normal. Why? Because we are dealing with a closed surface. Yes. So here let us consider the vector field F. Okay, when I draw a single arrow, you must understand that it is a field. Yes, let us consider the closed surface here. It is something like a mango. Closed surface. I will use the same shape throughout the subject to avoid the confusion. Let me put some dots here. Why I am putting these dots? To create the field that it is a three-dimensional one. Inside this one, there is a volume. Yes, there is a volume inside this. On this one, there is an area. For the closed surface, normal direction is always outwards. Okay, fine. So what is this divergence theorem is? It is closed surface integral of f dot dA is equal to volume integral of divergence of f into dV. This is a divergence theorem. So there is no headache of deciding the normal direction here. Why? Because you are dealing with a closed surface. The normal direction is always outwards. What it is? The normal direction is always outwards. Clear? Yes. So we have seen the divergence theorem and Stokes theorem and divergence theorem. When you are using the Stokes theorem, this is how you need to decide the normal direction. Clear? So this is an extension to the Stokes theorem. Now these are divergence theorem. Now let us have some questions here. Let us have one of the question. This was one of your previous question. Given V is equal to X cos square y x cap plus x square e to the power of z y cap plus z sin square y z cap and s the the surface of a unit cube with one corner at the origin and edges parallel to coordinate axis. The value closed surface integral of v dot n cap into ds is. This is a question. Yes. What is the integral? It is a unit cube. There is a vector field is given. Here is a vector field. V is equal to x cos square y x cap plus x square e to the power of z y cap plus z sin square y z cap. And S the unit cube with one corner at the origin and edges parallel to the coordinate axis. So what you need to find out? You need to find out this integral. And interestingly, what is this one? N dot ds is nothing but a ds. That is the explicit way of representation. Implicitly, what you will write? Just you will write it as a ds. So what is the integral is asking beta? Let us try to find the solution. So what is the integral is asking? Closed surface integral of v dot ds. Yes. So if you what is the surface here? What is the, let us consider the coordinate system here. Here it is the x axis, here it is the y axis, here it is the z axis. Here it is 1, 1, 1. Here it is a unit cube. And there is a vector field V. Is asking what is the closed surface integral. If you want to deal with this surface integral, total how many surfaces I need to perform? Total I need to perform 6 surfaces, isn't it? Because it is a cube. Top, bottom, left side, right side, that side, this side. Isn't it? Total it will have 6 faces. You need to perform total 6 times integration. Isn't it? And while you are performing the 6 times integration, you need to take care about the normal also. Suppose if you are dealing with this one, the normal is outwards. Why? Because this is a closed surface. Yes. So for this surface, the normal is like this. For this surface, normal is like this. Like this. Yes. So don't waste your time. Generally, whenever the questions are asked for the closed surface, go for what is called this divergence theorem. What is the divergence theorem here? Which is equal to volume integral of divergence of V into V. dV. Don't get confused with this V and that V. Here it is a vector V. Here it is a differential volume V. I have used the different symbol. So first find out the divergence of V. What is the divergence of V? Dou by dou x of x cos square y plus dou by dou y of x square into e to the power of z plus dou by dou z of z sin square y. What is divergence of V? Here it is cos square y plus 0 plus sin square y, which is equal to 1. Clear? Yes. Let me turn the page here. So you have got a divergence of V is equal to 1. So what is the integral beta here? I is equal to, let me go back. So here it is 1 into dV. You can directly write it as a volume. So what is it is indicating? Volume means what? 1 into volume of the box. It is 1. Or you can also write here it is dx, dy, dz. Separate out the variables. Here it is dx, here it is dy, here it is dz. X limits are from 0 to 1. Y limits are from 0 to 1. Z limits are from 0 to 1. So the integral is 1 into 1 into 1, which is equal to 1. Okay, let us take one more question. I'll going to turn the page. This was also one of your previous question, but in the EC paper. If A is equal to xy x cap plus x square y cap, then closed line integral of ADL over the path shown figure over the path shown in figure is here it is a x, here it is a y, here it is a loop given like this. The loop limits are given here. Here it is 1 by root 3, 2 by root 3, here it is 3, here it is 1. So how do you integrate this one? I is equal to closed line integral of ADL is required. If you go by this one, how many times integration you need to perform? 3 times. Over this section, this section, this section, this section. It is a waste of time. And you need to take care about the limits also. When you are dealing with this section, y is constant, x is ranging from 1 over root 3 to 2 over root 3. And over this section, and so on. So better that you have to use what is called a Stokes theorem. What is the Stokes theorem? Surface integral of del cross A dot ds. So find out the del cross A. Here it is x cap, dou by dou x. What is the x component here? It is xy. Here it is y cap, dou by dou y. Here it is x square. Here it is z cap, dou by dou z. Here it is 0. X cap into this into this minus this into this. So which is 0 minus 0. Minus y cap into this minus this into this. Here it is 0 minus 0. Z cap into this minus this into this. Here it is 2x minus x. So del cross A is equal to x into z cap. I'm going to turn the page here. So what is the integral here? Integral here I is equal to surface integral of x dot z cap dot dx dy z cap plus dy dz x cap plus dz dx y cap. So what is this one? Here it is z cap, here it is z cap. This entire thing is a 0. Here it is x into dx into dy. Separate out the variables. X into dx, here it is dy. Here it is x square by 2. What are the x limits? 1 over root 3 to 2 over root 3. Here it is y. Y limits are from 1 to 3. Upper limit minus lower limit. 4 by 3 minus 1 by 3. 3 minus 1. 1 is the answer. Okay. Yes. Yes, very good. Now let us take some break here. After the break, we're going to take some typical problems on the Stokes theorem and divergence theorem. And after that, we're going to start the coordinate system. In the today's system, we're going to start what is called a Cartesian coordinate system. Clear? Yes. Let us have some 20 minutes break. After the break, we'll continue. Okay, welcome back, friends. Let us consider this question. This was asked in the GATE EC paper for 2 marks. Given F is equal to zx cap plus xy cap plus yz cap. If S represents the portion of the sphere, what it is? If S represents the portion of the sphere, portion of the sphere x square plus y square plus z square is equal to 1 for z greater than 0, then surface integral of del cross f dot dA is, yes, any answers from your side? This was asked for 2 marks. Any answers from your side? Or you hope you are all are active? What is the answer? Come on, speak out. So you need to integrate this one. Curl under the surface integral. It is something related to the Stokes theorem. Curl under the surface integral is nothing but a closed line integral. If the surface S represents the portion of the sphere, any answers from your side? I have given options also. Yes, let us try to address this question here. There is a surface S represents the portion of the sphere. That too sphere is defined. X square plus y square plus z square is equal to 1 is a sphere. And z greater than 0 is a upper half of the sphere. That means it is a hemisphere. It is something like this. Here it is x-axis, here it is y-axis, here it is z-axis. Clear? Any answers from your side? Speak out. No one is giving answer. Yes. So here it is a contour. Here it is a surface. This is a S surface. This is a contour C. Let me turn the page here. So what is the integral he is asking in the question? The integral, listen carefully. A little bit visualization is required here. The integral here is surface integral curl of f dot dA, which is equal to, according to the Stokes theorem, which is equal to closed contour integral of F dot dl. But this surface is little bit complicated surface. We also know that this is also equal to, I have given in the extension in the Stokes theorem. I'll take the S naught surface. S naught surface is a flat surface. So this is also equal to del cross F dot dA. So what I'll do, instead of considering the bulged surface like this, I'll take the flat surface. Here it is X, here it is Y, here it is Z. Yes. Now here it is very easy surface. I'll call it as a S naught surface. Let me consider the small piece of area here. Here it is Z cap. Then what happens to the differential area? dA is equal to dA into Z cap. Okay. Yes. Now what I'll do? Now this is a very easy for us to use. I'm going to take this integral. Clear? So first I need to find out what is called del cross F. Is determinant of x cap dou by dou x. What is the x component? It is Z. Here it is y cap dou by dou y of y component is x. Here it is z cap dou by dou z of z component is y. Here it is x cap into this minus this into this, which is 1 minus 0, minus y cap into this minus this into this, which is 0 minus 1, plus z cap into this into this minus this into this, which is 1 minus 0. What is del cross F? X cap plus y cap plus z cap. So what is the integral? Integral I is equal to surface integral over S naught into del cross F dot dA. What is this dA? dA into z cap, which is S naught x cap plus y cap plus z cap dA into z cap. S naught into dA. Yes, so here it is z cap, z cap. What is this is indicating? This is indicating the area. Let me go back. What is the radius of this one? Here it is a unit radius, isn't it? So the radius of this one is 1. And what is the area of this one? Area is equal to pi r square, which is pi. So here it is. Pi is the answer. Clear? Yes. Little bit typical question this is. Yes. Let us take one more question. I'll going to turn the page. The vector field is described as F is equal to XX cap plus YY cap plus ZZ cap. Evaluate the net flux crossing. Evaluate the net flux crossing through the volume. Evaluate the net flux crossing through the volume x greater than 0 comma y greater than 0 comma z greater than 0 comma x square plus y square plus z square is less than or equal to 1. So what is asking? Come on, speak out. What it is asking? It is asking us to find out what is called net flux, isn't it? How do you find out the net flux? Net flux is nothing but a closed surface integral. Yes or not, beta? So what is the solution is asking for? Net flux. It is clearly mentioned in the question. Yes. So here it is psi net, which is equal to closed surface integral of f dot dA. But never perform closed surface integral. Go for what is called divergence theorem. What it is? Divergence of f dot dV. But before going into that, let us try to draw this one. It is a sphere, isn't it? X square plus y square plus z square is equal to 1. It is a sphere. But this sphere is defined, we are considering only for all x comma y comma z values greater than 0. That means in the first octant, for the 2-dimensional plane, you will going to get the quadrant. For the 3-dimensional plane, you will going to get octant. Just after this, we'll going to see the coordinate system. Okay. So if you draw those limits, how does it will going to look like? The entire sphere. It is only all the positive values, isn't it? It is called octant of the sphere, 1/8 of the sphere. Suppose if you have an apple like this, if you cut it like this, cut it like this, cut it like this, 3 cuts will lead to 8 pieces. How many pieces? 8 pieces. 3 cuts will lead to 8 pieces. I'll going to draw one of the piece here. So here it is x, here it is y, here it is z. It is a first octant here. For the 3D visualization, I am drawing like this. This is the first octet. It is an octant. Octant means what? 1/8 of the sphere. And what is the volume of this one? One by 8 into 4/3 pi r cube. It is 1 cube. So here it is pi by 6 meter cube. Keep this one aside. Let us proceed with this one. So to proceed with this one, you need to find out the divergence of F. What is the divergence of F beta? Is dou by dou x of x plus dou by dou y of y plus dou by dou z of z. Yes. Then what is the divergence of F? It is 1 plus 1 plus 1. Divergence of F is equal to 3. So what is the integral here? Net flux. Let me turn the page. Net flux is equal to volume integral of divergence of F into dV, which is 3 into dV, which is, you can bring that 3 outside. So what this is indicating? This is indicating what is called a volume. What is the volume which I have already kept ready? 3 into, how much is the volume? Pi by 6. So what is psi net? Pi by 2 is the answer. So these are the some of the typical questions. Okay, fine. Now let us turn the page here. Now we're going to discuss what is called a coordinate system. The first one is Cartesian coordinate system. If you open any textbook for the electromagnetic theory, you will going to start with the coordinate system. You will going to find the definition of the vector, definition of the scalar, Cartesian coordinate system, cylindrical coordinates, Cartesian okay, cylindrical little bit okay. When it comes to the spherical coordinate system, completely it looks like a imaginary subject. And that is where the students will lose the interest on this subject. So that is the reason why I have presented this subject in a different manner. We have started something with the motivation and vector calculus. Undoubtedly, the coordinate system is important for our exam. But you never get the direct questions on the coordinate system in any competitive exam. But what is here, the coordinate system is required in understanding our electromagnetic theory concepts. Suppose, for example, if you are dealing with a parallel plate capacitor, the best suited coordinate system is a Cartesian coordinate system. For example, if you are dealing with the coaxial cable, the best suited coordinate system would be cylindrical coordinate system. Suppose if you are dealing with the spheres, then the best suited coordinate system is a spherical coordinate system. So according to the electromagnetic theory problem, you need to choose the appropriate coordinate system so that you can understand the problem of the electromagnetic theory. So, in order to choose the appropriate coordinate system, basically you should know what actually the coordinate systems are. You should have the clear-cut visualization. You should have the clear-cut visualization of all the coordinate systems. Here we are going to have a discussion for the 3 coordinate systems. What is more important as far as the coordinate system is concerned is a visualization. Please pay your attention. It is not an easy thing like other things. Some attention is required to some extent. Please try to concentrate here. Let us try to focus on what is called a coordinate system. Clear? So first, obviously, we're going to deal with what is called a Cartesian coordinate system. These coordinate systems are developed based on how we are viewing this unbound medium. I can view this unbound medium as a box. Then that leads to what is called a Cartesian coordinate system. If I assume this unbound medium as a cylinder, then that leads to the cylindrical coordinate system. If I assume this unbound medium as a sphere, then that leads to what is called a spherical coordinate system. Based on how we are viewing the coordinates, how we are using this unbound 3-dimensional space, and that leads to the coordinates. Clear? Let us start with the very simplest possible coordinate system, what is called a Cartesian coordinate system. Clear, beta? Yes. So we'll be dealing with what is called Cartesian coordinate system. Here the coordinates are x, y, z. Here the limits are very simple, but you must be careful at one point. Here the limits are x is ranging from minus infinite to plus infinite. Y is ranging from minus infinite to plus infinite. Z is ranging from minus infinite to plus infinite. Here we are using what is called right-handed and orthogonal coordinate system. What it is, I'll justify in a moment. Right-handed, we'll be using what is called IEEE standard. Right-handed, what is better? Right-handed and orthogonal coordinate system. Right-handed and orthogonal coordinate system. What is the meaning of orthogonal? The meaning of orthogonal is x is perpendicular to y is perpendicular to z. We are dealing with the orthogonal coordinate system. And what is the meaning of right-handedness? I'll explain later. X, y, z. These three are orthogonal set. What does that mean? For example, x cross y is z and y cross x is equal to minus z. Then one can ask, why can't I take x cross y as a minus z? Why can't I take this circle in the anti-clockwise direction? That will be the left-handed coordinate system. We are dealing only here with the right-handed coordinate system. Throughout the subject, we'll be following what is called a IEEE standard. I'll justify that one in a moment. I'm going to turn the page here. So how this Cartesian coordinate system is developed? By assuming this unbound three-dimensional space as a box. And if you draw a three lines from the corner, it will going to form a three axis. They are x comma, y comma, z axis. Yes. See, this is a story like this. Here it is x axis, here it is y axis, here it is z axis. Yes, this is developed by assuming this unbound medium as a box. Clear? Yes. Observe here. Suppose if I want to locate some particular point P here, that point P will have a three coordinates. Yes, if you want to reach this to this point, I need to move along the x, along the y, along the z to reach that point. Isn't it? So I need to move along to reach this point. What I have to do? I need to adjust the x value, I need to adjust the y value, and I need to adjust the z value. Clear? Yes. So that I want to frame a vector from here to here. Yes, that is the point P, let us say. It is having coordinates x comma y comma z. I want to decide the directions of unit vectors. What are the directions of unit vectors? These are the vectors with the magnitude 1 oriented along the x comma y comma z directions. Here it is the x axis. Here it is the y axis. Here it is the z axis. This is point P. Clear? Let me consider the small piece of area here. What happens to this area? This area will be dA is equal to, that is in the YZ plane. It is dy into dz into x cap. This one beta. This is in the xy plane. Sorry, y is constant. That is zx plane. dA is equal to dx into dz into y cap. The area direction is like this. Here it is x cap. Here it is y cap. What happens to the differential area? Dx into dy into z cap. Now let us focus on, anyhow you can notice that the electric field is perpendicular to magnetic field is perpendicular. Sorry, I am really sorry. X is perpendicular to y is perpendicular to z. These are the unit vectors here. Here it is x cap, y cap, and then z cap. Okay, this is a very simplest possible coordinate system. Clear? But let us focus on this right-handedness. That is little bit, you need to think about this one. Right-handedness, come on, focus. You need to answer my questions. The right-handed coordinate system. See here, I have fixed the x here, y here, z here. Is that fixed? Or can I interchange their positions? I can interchange their positions. I can make this as x, this as y, this as z. But you need to follow the right-handedness. What is the meaning of right-handedness? If I rotate my fingers from x to y, my thumb will point z direction. If I rotate my fingers from y to z, right hand. If I rotate my, listen carefully, if I rotate my fingers from x to y, my thumb will point in the z direction. If I rotate my fingers from y to z, my thumb should point in the x direction. If I rotate my fingers, right hand fingers from y, z to x, my thumb will point in the y direction. Clear? Yes. Listen carefully. So this right-handedness, x cross y is z, y cross z is x outside, or z cross x is y, right side. This right-handedness can be explained easily with the help of what is called a mechanical screw. Before that, let us have like this. Hope you know the vector is represented with the arrow. Here it is a tip of the arrow. And this is called a tail of the arrow. If the vector is coming towards us, what I'll notice, we'll notice the tip. It is towards us. If the vector is going into the board or into the paper, we'll notice the cross or a tail. It is away from us. Okay, let us, I'm going to give some examples, 6 examples. So from there, you'll understand what is this right-handedness. I'll repeat one more time. If I rotate my fingers from x to y, my thumb will be in the z direction. Clear? If I rotate my fingers from y to z, my thumb will be from x, in the x direction. If I rotate my fingers from z to x, my thumb will be in the y direction. Right-handedness. So this right-handed principle can be easily explained with the help of what is called a mechanical screw. Let me turn the page here. The mechanical screw will best explain this one. Here it is x-axis. Here it is y-axis. Here it is z-axis. This is a right-handedness. What is the mechanical screw? Here is a mechanical screw. If I rotate my mechanical screw like this, it will go down like this. If I rotate my mechanical screw like this, it will go down like this. If I rotate like this, it will come up like this. So the bottle cap is a best example for mechanical screw. Bottle cap. If I rotate like this, observe here carefully. If you do not understand this one, you cannot understand the right-handedness. It is a very simple thing, but you need to focus on that. Listen carefully. If you have mechanical screw, just take a bottle, just to rotate like this. If I rotate like this, it will go up. If I rotate like this, it will go down. If I rotate like this, it will go up. If I rotate like this, it will go down. That is a mechanical screw. That means, see here, how to make a use of mechanical screw. Mechanical screw is giving the right-handedness. Suppose if you want to get the direction of Z, what I need to do? I need to rotate the mechanical screw from X to Y. So wherever it is moving, that is the direction of Z. If you want to get the direction of X, you need to move the mechanical screw from Y to Z. It looking simple, but let us take some examples here. Now you must answer them. Number one, we'll start with a simple thing. X is like this, Y is like this. Number two, X is here, Z is here. Number three, Y is like this, Z is like this. Yes. Come on, please answer. For the first one, what is the direction of Z? Is it inside or outside? Come on, speak out. I want answers from your side. Come on, speak out. Yes, beta. Inside. Very good. Inside. You have to, everyone should think about this one. Come on, speak out. I want a direction of Z. So if I want a direction of Z, I should rotate my screw from X to Y. So first case, X to Y, like this. If I rotate my screw from X to Y, what happens? The screw will go inside, isn't it? Yes. So that is the direction of Z. Second one, I want a direction of y. Come on, speak out. What should I do? Come on, everyone should answer. Second one, everyone should try. What about second one? Second one is out. Yes, very good. I want the direction of y. So if you want the direction of y, I should rotate my screw from z to x. Z to x means what? You need to rotate like this. Z to x. If I rotate my screw like this, it will come outside. So this is the direction of y. Third one, beta. I want the direction of x. I need to rotate my screw from y to z. Like this. Y to z. So it will go inside. These are the simple examples. Let us little bit complicate this one. Number 4. X is outside, y is like this. Number 5. Everyone should understand this exercise. Here it is z cap. Here it is y cap. Number 6. Y cap. X cap. This is left side, this is right side. So what is the direction of Z for the fourth one? Come on, speak out. Left or right? See here, if this is the case, you need to take the help of one pen here. Most of the students are not comfortable with this one, I know, but I need to discuss. It is not that all the easy things I can discuss and everyone will clap and go out. That will not going to help in our exam. Gate understanding means you need to understand up to the level of gate exam. I know that this is hard to visualize, but you must understand it. See here, beta, it is like the thing. What is the fourth case? The x is coming outside like this. X is coming outside, y is like this. So what should I do? For the direction of z, I should rotate my screw from x to y. I should rotate my screw like this. Here it is a x. Here it is a. So here it is a. Here this is a x. This is a y. I need to rotate my screw like this. X to y. If I rotate my screw like this, it will go inside. Isn't it? Inside means which direction? Like this. Is it clear? Or you can look at this problem. This is x is like this, beta. You are looking from this side. You can also look the same problem from here also. This side. X cross y. This is x. This is y. X cross y, it will come outside. Outside means z direction, like this, left side. Come on, what about the fifth one? Give the number and give the answer. Left side or right side? Fifth one. Fifth one. Left or right? Fifth one. Fifth one is also same story. For the fifth one, y is going inside, z is like this downwards. To get the direction of x, what should I do? I should rotate my screw from y to z. Y to z. Y is inside, z is like this. So here it is y cross z. If I rotate my screw from y to z, it will come outside. Yes, outside means which direction? Like this. What about the sixth one? If you do not try this one, you cannot get this one. You need to try. Take some the help of the two pens and try to decide. That's all it is. Nothing more than that. If you do not practice, you do not get this one. It looks very simple. What is the sixth one? Why I am giving these many examples is, if not in a one example, in other example, this idea will strike you. Strike your brain. See here, y is like this. Y is outside. Here. You want a direction of z here. So I should do x cross y. X is downwards, y is outside. X cross y. X cross y, it will come outside. Means left. Next. Seventh one. Eighth one. Ninth one. Tenth one. Come on, speak out. Seventh one. Seventh one is also same story. That means here the z is going inside, y is like this. Z is going inside, y is like this. So here it is y cross z. It will come outside. You go, if you want to get the direction of x, y cross z. Y cross z, it will come outside. Outside means which direction? Left side here. What about eighth one? X is going inside, z is like this. If you want to get the direction of y, what you have to do? Z cross x. Z cross x, again it will come outside. Outside means left side. Ninth one and tenth one. Come on, speak out. Give the number and give the answer. Ninth one and tenth one. Give the number and give the answer. What is the ninth one? top or bottom, top or down, upwards or downwards. Ninth one is up, 10th one is also up. Let us see. See here, same story. For the ninth one, you want to decide the direction of y. Here it is z cross x. X is like this. X is towards us. X is like this, Z is like this. So to get the direction of y, I should rotate Z cross y. Here it is Z, here it is X. Z cross X, it will go up. What about the 10th one? Z is inside the board, Y is like this. So this is Z, this is Y. If you want to get the direction of X, you need to rotate Y cross Z. Y cross Z is going up. So that is the direction of. So we'll be using this right-handed coordinate system throughout our subject. Still, if you have a problem in deciding, there is no other way. You need to take 2 pens and try to familiarize yourself with the mechanical screw. Just to take your water bottle cap and rotate like this and try to familiarize yourself with that. So once you familiarize, you can use that one. That is only the way which will help you. Take your 2 pens and try to familiarize the mechanical screw and try to decide. So this is all about the Cartesian coordinate system. Let us discuss what is called a cylindrical coordinate system. Number 2. Cylindrical coordinate system. Here the coordinates are rho, comma, phi, comma, z. Suppose if I assume this unbound 3-dimensional space as a cylinder, then if I want to locate some particular point P on the cylinder, again I need the 3 coordinates. They are rho, comma, phi, comma, z. Here the limits are, I'll justify them later. Rho is ranging from 0 to infinite. Phi is from 0 to 2 pi. Z is from minus infinite to plus infinite. Rho is the radius of the cylinder. Phi is called azimuthal angle. Z is axial length. Okay, what they are, I'll justify. And one more thing, here also we are using a right-handed and orthogonal coordinate system. What it is? Right-handed and orthogonal coordinate system. Right-handed and orthogonal coordinate system. Here it is, rho is perpendicular to, phi is perpendicular to z. And what is the meaning of right-handedness? Same story. Rho cross phi cross z. This is an orthogonal set. For example, rho cross phi is Z. If I do reverse, phi cross rho is minus Z. There is a note here which is taken from your mathematics. Angle direction is tangent direction at that point. Angle direction is tangent direction at that point. Okay, let us draw the coordinate system here. I'm going to turn the page. So if you assume the cylinder will have the axial length, isn't it? And cylinder will have a cross section. What kind of cross section it will have? Circular cross section. Now I want to locate some particular point P on the cylinder. Again, I need three coordinates. They are rho comma phi comma z. Okay, fine. So what I'll do, I'm going to take the Cartesian coordinate system is a very fundamental coordinate system on which the remaining coordinate systems are defined. So while going to draw what is called a right-handed Cartesian coordinate system. Here it is x-axis, here it is y-axis, here it is z-axis. So now you are having some cylinder here. Cylinder will have an axial length. Now I'll take the cylinder and I'll going to align the axis of the cylinder along the z-axis. That means I'll going to place my cylinder like this. So the axis of the cylinder is along the z-axis and the surface of the cylinder is in which plane beta? XY plane. Okay, fine. Now I want to locate some particular point P here. That point P will have three coordinates. They are rho comma phi comma z. What is that rho? Rho is a radius. If I drop this point onto the XY plane, this is also rho. The angle made with respect to x-axis is phi, and the distance from here to here is z. Okay, so let me show you something like this. This is rho radially outwards. So this is angle phi, and this is axial length. Let me go back. What is this one? Rho. Rho is a radius of the cylinder. It is ranging from 0 to infinite. And what is this phi? It is 0 to 2 pi. And z is the axial length, which is from minus infinite to plus infinite. Clear beta? This is rho. This is also rho, isn't it? So how it is? Observe here. This is rho. If I drop this one onto the xy plane, this is also rho. Angle made with respect to x-axis is phi, and the axial length from here to here it is z. Clear? Just a minute. Yes. I want to decide the directions of unit vectors. What are the directions of unit vector? Anyhow, rho is radially outwards. Z is along the z direction. Then what is the angle direction? Angle is like this. So angle will be tangent at this point. Let me go back here. So this is from your mathematics. What is the angle direction? Angle is a tangent direction at that point. So to decide the angle direction, I will going to draw the top view of this one. Let me turn the page here. Suppose if I see a top view of a cylinder, what I will notice? I will notice a circle in which plane beta? XY plane. Let us draw a top view here. Here it is x-axis. Here it is y-axis. Here it is z-axis. Okay. Here it is a circle. Yes, beta. This is what? This is a radius is. Radius is rho. Angle made with respect to x-axis is phi. So how the radius is defined? Here it is radially outwards. Phi is like this. I want to define here. I want to define here angle all the directions. I want to define here. I want to define here. What happens here? Z is anyhow outside the board. Clear? Rho is radially outwards. Z is phi is tangent at this point. Z is outside. So the ray Z is outside here like this. Rho is radially outwards. Z is like this. Sorry, phi is like this. Angle is tangent at this point. Z is outside. Z is outside here, beta. Rho is radially outwards. Angle is phi like this. Tangent at this point. Z is outwards. Z is outside like this. Rho is radially outwards. Phi is tangent at this point. Z is anyhow outwards like this. Let me go back. How can I show here unit vectors? Rho is radially outwards. Z is in the Z direction. Angle is tangent. Clear? Yes. So the angle is tangent at that point. Clear, beta? Yes. So here it is. Rho is radially outwards. Z is like this. And phi is tangent at this point. Here it is rho phi z. This is point P. Rho is perpendicular to the phi is perpendicular to the z. Clear? Yes. So it is an orthogonal coordinate system beta. Now let us consider conversions here. It is very easy to do the conversions. I want to convert it from rho comma phi comma z to x comma y comma z beta. See here beta, it is a very straightforward here. Rho is making phi angle with the x axis, or otherwise you can also notice here. This is rho, this is also rho beta. So what is the x component beta? X component is equal to rho cos phi. Y component is rho sin phi. Z is anyhow z. So it is very straightforward. Rho is equal to, x is equal to rho cos phi. Y is equal to rho sin phi. Z is anyhow equal to z. I want to do reverse beta. X comma y comma z to rho comma phi comma z reverse. You can check out here. Rho is equal to square root of x square plus y square. Phi is equal to tan inverse of y by x. Z is equal to z. Clear? Yes. You can see animation videos. Google images are available for all these things. Okay, beta. So this is all about the cylindrical coordinate system and as well as the point conversions. Now the session will be open for your doubts. Just raise your hand. I will come to you. You can ask me the questions. I'm comfortable with Hindi and Telugu as well. If you want, you can ask in those languages. Feel free. Yes, Vishnu. No form, please. Direct go to the question.
Yeah, sir. My question is one thing while explaining surface integrals, you did mention a point that a closed surfaces enclose both the in and out, something you mentioned, sir.
Closed surface will have the inflow as well as outflow.
Yeah, exactly, sir. I couldn't get that meaning, sir.
Simple observation that is. Here I have considered the open surface, right?
Yes, sir.
Open surface will have only the flow. Suppose if you have a balloon-like thing instead of this.
Yes, sir.
There will be inflow and outflow, which leads to the net flow.
I mean, inflow and outflow. That's what I'm. Here also there's an inflow and outflow. I mean, okay, here the entire thing is coming and going out, so it is net flow 0.
Same surface. For this, if you have a closed surface like this, see. If you have a box like this, let us say some liquid is entering from here and leaving from here.
All right.
For this one, the normal is this side.
Yes, sir.
For this one, normal is
The side.
minus inside. Suppose if I write, let us consider this as a S1 surface, this is a S2 surface.
Yes, sir.
Suppose if I write this as a closed surface of some vector f dot dA. Surfaces are not contributing for any flow. Only S1 and S2 surface. Total it is having a 6 surfaces, but only S1 f
And
dot.
S2 DA.
Just a minute. It is N1.
Plus N2.
This is N2
Okay, sir.
plus S2 f dot dA. How this can be written? S1 f dot dA into n cap minus S2 into f dot
DA and cap.
n cap. So here it is a flow from the surface S1 minus surface S2. So which leads to net flow.
Sir, but again, the thing is, anything that is entering through surface 1 and leaving through surface 2, both are same only, no, sir? Actually, strictly speaking, there's nothing.
That depends on the vector field. The deformation of the field may happen. Who knows?
Oh, in between the surface between S1 and S2.
S2. The field some field may be accumulated inside the box. That depends on the nature of the field.
Okay, sir. Okay, sir. So that's why you meant that there's a net flow in the closed surfaces.
This is a mathematical proof for the net flow. From the closed surface, net flow happens. From the open surface, there won't be any this one.
Only there will be one surface.
Only one surface, there will be a flow.
Okay, all right, sir. Thank you, sir.
Okay, better. Bhimal and do.
Yes, sir. Good evening, sir. Sir, in that problem, that EC question, that answer is pi. Here we can write f has 0 I cap plus cos. Yes, yes. From that, okay, sir. Here f dot dl over closed integral Stokes theorem also we can use.
Stokes theorem, closed line integral.
F dot dl.
Closed line, for using this one in the closed line integral, you convert
yes.
this cylindrical form.
Okay. That x will be 1 cos theta, y will be 1 sin theta, and z will be 0.
That is also you can do.
Okay. Okay. Here also, sir, okay. One equation that z0 x square plus y square is equal to 1. Something.
But this will become mathematically trivial, mathematically lengthy.
Lengthy?
Why? Z is also there.
What is z? We are putting 0.
Z is equal to 0, yes.
Then r cos theta. Only one term of j term will come. Okay. Thank you.
Yes, you can go in that way also. Good. All these are mathematical techniques anyhow.
Thank you.
Right, beta. Mohammad Mubin.
Sir, ये closed surface, open surface, closed line, closed contour, open contour का एग्जाम क्लैरिटी नहीं आ रहा सर.
इधर देखो. लाइन को कॉन्टूर बोलते बेटा. कॉन्टूर का मतलब है लाइन. ये लाइन है ना?
हाँ सर.
ऐसा है. ये ओपन है या क्लोज्ड है?
ओपन.
ओपन है. इसका इनिशियल पॉइंट है और फाइनल पॉइंट है. इसका कोई सरफेस नहीं है.
हाँ सर.
मगर ये क्लोज्ड हुए तो इसका सरफेस आ गया.
हाँ सर,
मतलब इसका मतलब है क्लोज्ड कॉन्टोर के अंदर होगा सरफेस। वो भी कौन सा सरफेस है भाई? ओपन सरफेस है। ऐसा ओपन सरफेस है, ऐसा हो सकता, नहीं तो ऐसा भी हो सकता। ये क्लोज्ड कॉन्टोर है ना यहाँ पर। सो क्लोज्ड कॉन्टोर इस एनक्लोजिंग, कौन सा तरह का सरफेस एनक्लोज कर रहे हैं यहाँ पर? ओपन सरफेस। आप समझ में आया?
हाँ सर। सर अब
और देखो
क्लोज्ड, हाँ सर,
ये सरफेस है, ठीक है। ये कौन सा तरह का सरफेस है? ओपन सरफेस है ना।
ओपन,
ओपन सरफेस एनक्लोज हो गया तो समझो ऐसा हो गया। इसके अंदर क्या है? वॉल्यूम है। तो क्लोज्ड सरफेस एनक्लोज, ओपन सरफेस एनक्लोज हुआ है तो सरफेस एनक्लोज हुआ है तो इसके अंदर होगा वॉल्यूम। अरे व्हाट, ऐसा है, बैलून का जैसा है। क्लोज्ड सरफेस एनक्लोजेस वॉल्यूम। देखो बैलून, बैलून ओपन सरफेस है या क्लोज्ड सरफेस है?
क्लोज्ड।
हाँ, क्लोज्ड सरफेस के अंदर क्या होगा? वॉल्यूम होगा।
ओके सर, वही स्टोक्स थ्योरम और डाइवर्जेंस थ्योरम वही चेक। ठीक ठीक है सर, आपका क्लैरिटी है सर।
चलो ठीक है। प्रत्युषा बोलिए बेटा।
Hello, sir. Sir, can you explain this closed line integral is same as open surface integral, sir?
हाँ
And the closed surface integral is same as volume integral.
हाँ, not
Sir.
same.
Yes, sir.
The divergence and Stokes theorem, they are same.
Sir, means the statement meaning of the closed surface is
They are not same. They are, there is a Stokes theorem here. Closed line integral is related to. Here, closed line. Inside the closed line, what is there? Open surface is there.
okay. Sir, just now you explained that one only, sir.
But what's your doubt?
Sir, first I also didn't understand that one, sir. How closed line is an open surface.
Now is it clear?
Yes, sir. Yes, sir.
Okay, better.
Hello, sir. Slide number 54.
54. बेटा.
Sir, 9. Okay. Okay, sir. Understood. I wrote down wrong. Thank you, sir.
Take 2 pens if you get a doubt. Explain this one. For the next one, you need to think, isn't it? You have to practice. You have to think about that. If you do not think about that, you cannot get.
Sir, understood.
Okay, I'm talking in general. आशा बोलिए बेटा.
Hello, sir.
Yes, बेटा बोलिए.
Sir, page number 40. Sir, next. 40, sir. It's
पीछे
a 41.
ये है ना.
Sir, in this. Sir, how we take the direction of the normal, sir? Because you are telling that if you go from top to bottom, it's take right side.
Top to bottom नहीं बेटा. अब गलत फहमी हो गया. इधर देखो.
Sir, in closed surface, sir.
ऐसा मैंने कुछ नहीं बोला. Top to bottom, bottom to top. ऐसा मैंने.
No, sir. Means it's going downward, no, sir. That
सुनिए.
anti-clockwise direction.
Just listen. इधर देखो, लूप डायरेक्शन ऐसा है.
हाँ yes sir.
समझो लूप का डायरेक्शन ऐसा है तो आपका फिंगर्स कीप योर फिंगर्स इन द डायरेक्शन ऑफ लूप का डायरेक्शन में आपका फिंगर्स को लगा दीजिए. जो थंब का डायरेक्शन होगा वो नॉर्मल बनेगा.
The thumb is going downwards.
थंब ऊपर आ गया. लूप डायरेक्शन में आपका फिंगर्स को लगा दीजिए. थंब का
ठीक है.
नॉर्मल मतलब बाहर आएगा. समझ में आया?
Sir, I'm unable to connect this sir.
आप लिखिए, पेपर के ऊपर लिखो.
Okay sir.
लिख के लूप का डायरेक्शन ड्रॉ करो.
Yes sir. Edit sir.
सब फिंगर लगा दीजिए तो थंब किस तरफ दिखाई दे रहा है आपको?
Upward.
अपवर्ड मतलब नॉर्मल ऐसा आएगा. इधर देखो, समझो लूप का डायरेक्शन ऐसा है तो आप फिंगर्स ऐसा लगा दीजिए तो
Yes sir.
थंब
Downward.
कहाँ वो इनसाइड होगा ऐसा.
Yes sir. I got sir.
ये सब्जेक्ट में लैंग्वेज होना चाहिए अच्छा, उसके साथ साथ बॉडी लैंग्वेज भी होना चाहिए.
I thought that direction of the thumb sir. That direction.
नहीं
I
नहीं
got sir. It's the direction of fingers.
हाँ डायरेक्शन ऑफ फिंगर्स है.
Sir, one more sir.
ओरिएंटेशन बहुत important है. हाँ बेटा बोलिए.
Sir, in page number 54.
54 हाँ बेटा बोलिए.
Sir, in this fifth one,
हाँ
that X must be right side no, sir.
let us check why you doubt.
Because it's inside, no sir. Means Y is inside.
हाँ सुनिए सुनिए listen. We want X बेटा, so I should cross Y cross Z बेटा, है ना? सुनिए बेटा.
हाँ yes.
अंदर है.
Sir, I imagination as the screw, sir, because I.
So Y like this, Y is like this, and Z is like this. If I rotate the screw from Y to Z, sorry, like this inside. Y is inside, Z is like this, Y to Z. If I do like this, the screw will come out. Come out means in the left direction.
Okay, sir.
और बताओ.
Sir, one more, sir. In question where we got to pi by 2, no, sir.
Question pi by 2.
Sir, in that how we take 1 by 8, sir? I am unable to get that 1 by 8.
1 by
8 volume is 1 by 8 into 4 by r. Why you take 1 by 8?
लिमिट्स देखो, लिमिट्स देखना चाहिए, थोड़ा विजुअलाइजेशन चाहिए यहाँ पर. 2 डायमेंशन में क्या होगा? क्वाड्रेंट होगा. In the 2 dimension you will get a quadrant, है ना? 3 dimension में क्या होगा? ऑक्टेट होगा. टोटल 8 पीसेस आएगा. 2 डायमेंशन में
2.
4 पीसेस होगा बेटा. इधर देखो.
Opposite माने से.
ऐसा इधर देखो. 2 डायमेंशन मतलब ऐसा 1 2 3 4. ये 2 डायमेंशन के लिए. 3 डायमेंशन में क्या होगा देखिए. पूरा कितना होगा? 8 पीसेस होगा. 1 और उसका पीछे 1 2 3 ऐसा 1 2 3 4 और नीचे सेम.
Okay.
So it is something like an apple. If you cut the apple, 3 cuts will lead to 8 pieces. I would run one of the piece. All the values are positive here. All the values are positive here. That is what mentioned in the question. Clear?
Yes, sir. I got it. Thank you so much.
Fine, fine. Have a nice day. Nice day, concept. Good night. बोलना चाहिए. हाँ बेटा.
Sir,
हाँ मत भाई बोल.
the surface formed by the closed contour, it may be any surface, the answer will be same, sir.
Answer will be same. That is a Stokes theorem. In the Stokes, it is only true for the Stokes theorem, beta.
Sir, it means in question he may give if a closed contour is given in a question and he had given it in a different shape, then we can reduce it to two-dimensional and we can solve it. Okay. Sir, can you tell a bit more practical about this, sir? I mean, I got this point, but
What practical about Stokes theorem?
About this surface and how it's coming, how the flux lines are going. Because surface means flux only, na, sir. Flux lines going and into that thing.
You will get all these things in your mathematics, but since you have asked, I'll explain. But before that, let me answer. Be on the line, Mohammed.
Yes, sir.
Our fellow friends are raising hands. Let me clarify them. Yes, Kushal.
Hello, sir. So in the line integral concept, all the field is shown. So means all the field is all the fields are aligned along the integral line integral, ना sir?
ऐसा मैंने कुछ नहीं बोला. मैंने बोला था कि एक फील्ड है. सुनिए देखो.
Yes, sir.
रीजन में फील्ड है. हिंदी समझते हैं ना?
Yes, sir. हाँ.
देखिए, एक रीजन में फील्ड है, तो मैं क्या करना चाह रहा हूं वहां पर, वो फील्ड को ये कॉन्टोर से मल्टीप्लाई करना चाह रहा हूं.
Yes, sir.
ऐसा भी हो सकता, ऐसा भी रह सकता, ऐसा भी रह सकता, ऐसा भी रह सकता, कैसा भी हो सकता.
सर तो मल्टीप्लाई करने के बाद सर मतलब जहाँ काउंटर है वहीं से तो फील्ड जाएगा ना.
वहां पर इक्विवेलेंट कितना है वो फील्ड आएगा. पर डॉट प्रोडक्ट ले रहे.
वही बोल रहा हूँ सर, मतलब जहाँ से लाइन जा रही है वो लाइन के अंदर से फील्ड दिखा रहा, उतना दिखा रहा है.
उसका इक्विवेलेंट है बेटा. इस छाया छाया शैडो शैडो. डॉट प्रोडक्ट का मतलब है शैडो, है ना. इसके ऊपर शैडो कितना है, इसका छाया इसके ऊपर कितना है, और इसका छाया किसके ऊपर कितना है, शैडो. नहीं तो आप इक्विवेलेंट बोल सकते.
इन द प्लेस ऑफ काउंटर देना सर, इन द प्लेस ऑफ काउंटर जितनी फील्ड जा रही है उतनी दिखाएंगे ना.
हाँ वही.
मतलब ये जो सीक्रेट जो फील्ड की डायरेक्शन ही दिखा रहा, उसमें से दिखा.
फील्ड की डायरेक्शन नहीं है बेटा. डॉट प्रोडक्ट का आउटपुट तो स्केलर है.
हाँ सर, स्केलर.
हाँ, फिर केवल उसका क्वांटिटी कितना है, क्वांटिटी का
हाँ
देगा.
ओके. एंड सर सरफेस में भी वैसे ही है ना, सेम सर.
सरफेस का मतलब अलग है. इंटीग्रल कितना वेक्टर फील्ड क्रॉस हो रहा है सरफेस से, वो है सरफेस इंटीग्रल. कितना क्रॉसिंग है.
ओके.
वो टेक्निक फ्लक्स कहा जाता है.
एंड सर जो वो क्लोज काउंटर और एरिया में सर क्या डिफरेंस बताया सर आपने?
कुछ फर्क नहीं है. क्लोज्ड कंटूर का अंदर सरफेस होगा, एरिया होगा.
हाँ वही ना सर, मतलब जो अंदर से जाएगा फ्लक्स वही एरिया में ही है ना, सेम है ना वही.
हाँ वही है.
इनसाइड और आउटसाइड में. और सर जो हमने डायग्राम देखे सर, आप ये S0 S1 आपने कहा इन्हीं शेप में, वो ठीक से समझ नहीं आया कि सर मतलब वो एक क्लोज काउंटर है ना वो. वो क्लोज काउंटर को आपने कैसे मतलब अलग शेप में डाल ये क्या, वो 3D हो गया ना, फिर सिर्फ 2D था, 2D है ना वो.
क्या बेटा? क्लोज काउंटर
जो है S0 S1 जो डायग्राम दिखा है आपने.
और क्लोज्ड काउंटर है, सही है, सही बोला आपने।
हाँ सर, तो उसको मतलब जो आपने अलग अलग शेप दिखाया वो कैसे क्या हो गया वो? हाँ ये इसमें सर,
ये जो मेरा हाथ में कप है, ये ओपन है या क्लोज्ड है?
ये ओपन है सर,
हाँ,
सरफेस।
ओपन है। इसका कांटोर है, ये कांटोर है, बोल सकते हैं ऐसा?
यस सर, हाँ
इसका
उतना सरकमफेरेंस उतना।
कांटोर बोल दो
हाँ हाँ,
इंटीग्रेशन भाषा में। ये क्या है, क्लोज है या ओपन कांटोर है?
ये सर ये काउंटर में सिर्फ सरकमफेरेंस आएगा या पूरा सिलेंडर आएगा सर?
कांटोर, सुनिए, नया शब्द क्यों इंट्रोड्यूस कर रहे हैं आप? मैंने क्या पूछा, ये ओपन कांटोर है या क्लोज्ड कांटोर है?
ये क्लोज काउंटर है सर।
क्लोज्ड कांटोर है, तो इसके ऊपर एरिया ऐसा है, ये पूरा ओपन सरफेस है ना?
यस सर, हाँ।
एक कांटोर से दूसरा एरिया क्या हो सकता?
हाँ सर,
इसको ऐसा दबाओ, एक दबा, इसको बनेगा ना?
हाँ सर,
कांटोर तो वही होगा, मगर डिस्क आएगा।
ओके।
वही कांटोर से और एक सरफेस क्या बना सकते हैं? ऐसा तो शेप अलग भी, दूसरा शेप ऐसा भी हो सकता था।
ओके, तो फिर सर फील्ड तो मतलब जो आंसर आएगा वो तो चेंज हो जाएगा ना?
स्टोक्स थ्योरम में चेंज नहीं होगा, वही तो है ना?
वही समझ नहीं आ रहा सर, मतलब उसमें से जो फील्ड जाएंगी वो तो चेंज हो जाएंगी ना?
चेंज होगा, मगर स्टोक्स थ्योरम सेम होगा, स्टोक्स थ्योरम वही रहेगा, वही तो है ना स्टोक्स थ्योरम का। सरफेस कौन सा भी रहने दो, मगर कॉन्टोर सेम है तो उसका कर्ल अंडर द सरफेस इंटीग्रल सेम होगा, वही तो स्टोक्स थ्योरम है।
मतलब सर उसका मैग्नीट्यूड सेम, ये सेम आएगा सभी तरफ?
इधर देखो, आपका स्टोक्स थ्योरम वहां मैंने कर कैलकुलस से लिया था, तो क्या पूछ रहे, प्रूफ है ना? स्टोक्स थ्योरम
हाँ।
इंटरप्रिटेशन बताना चाहिए। इधर मोहम्मद जी पूछता, मोहम्मद, होप यू आर ऑन द लाइन।
Yes, sir. I am.
इधर देखो बेटा, of FDL is equal to surface integral of del cross F dot dA। ये कांटोर के ऊपर ये सरफेस है, कांटोर ऐसा ले लीजिए बेटा, ये कांटोर है, इसके अंदर मैं कर्ल ले रहा हूं यहाँ पर, ये तो क्लोज लाइन इंटीग्रल है, मतलब ये है, इसके अंदर कर्ल ले रहा हूँ। कर्ल का मतलब क्या है, नेट रोटेशन पर स्मॉल एरिया, है ना? स्मॉल स्मॉल रोटेशंस ले लो, ऐसा समझो, लूप का रोटेशन ऐसा है, स्मॉल स्मॉल रोटेशंस ले लो ऐसा। पूरा कर्ल किसके ऊपर लगाया, सरफेस के ऊपर।
यस सर।
ये पूरा मैथमेटिक्स है, ऐसा पूरा कर्ल सरफेस के ऊपर स्प्रेड हो गया। तो क्या हो रहा है यहाँ पर, आपने कर्ल को पूरा सरफेस के ऊपर स्प्रेड कर दिया। ये जो कॉमन है, वॉट एवर द कॉमन इज देयर, दे विल कैंसल आउट। हियर इट इज गोइंग दिस साइड, हियर इट इज कमिंग दिस साइड, दिस विल कैंसल, दिस विल कैंसल। What actually remains is the outermost one. All the inner circulations will cancel out.
Okay.
So when the inner circulations are cancelling out, whether it is a flat surface or whether it is a bulged surface, it doesn't matter. All the inner circulations will cancel out. What actually remains is the outermost one.
Okay. Sir, हम काउंटर को काउंटर रोटेट ले रहे क्या? रोटेटिंग?
हाँ रोटेटिंग ले रहे.
ओके.
Sir, a small doubt. Sir, that rotations are field only, na sir?
हाँ field only.
Field only. Okay. Okay.
And sir, in the hemisphere question,
सुनिए
we have take
उतना आपको ये पूरा डिटेल डिस्कशन आपको मैथमेटिक्स में मिलेगा ये पूरा मैंने, मगर हमारे को क्या होना चाहिए, केवल स्टोक्स थ्योरम डाइवर्जेंस थ्योरम का एक्सटेंशन पता होना चाहिए और उसको कैसा इस्तेमाल करना हमारा इलेक्ट्रोमैग्नेटिक थ्योरी में वो है. अब बोलिए, उसीलिए तो मैंने इसका एक्सप्लेनेशन नहीं किया था.
ओके. हाँ सर, इन द हेमिस्फीयर में सर हम कौन सा भी सरफेस ले सकते हैं या फिर जो सर्कुलर सर्कमफेरेंस था वो लिया ना हमने, इसलिए नॉर्मल उसका नॉर्मली क्यों लिया, मतलब बाकी का सरफेस के लिए सर?
क्योंकि वो आसान है, डिस्क आसान है ना.
हाँ हाँ.
इसको ऐसा फ्लैट सरफेस है, उसको एकदम दबाया मैंने, दबाया तो डिस्क का, और डिस्क बहुत आसान है.
ओके.
तो मैं तो नहीं तो ऐसा सरफेस लिए तो ऐसा सरफेस लिए तो भी ऐसा भी आंसर होगा, मगर
ओके. सर इस सरफेस में से जो फील्ड जाएंगे वो तो सेम ही रहेंगे ना सर?
हाँ
मतलब
होगा.
पैरेलल ही रहेंगे ना, पैरेलल.
हाँ
ओके.
वो फील्ड के वो बाद में क्लैरिटी मिलेगा आपको.
ओके ओके ओके, ठीक है.
राइट. एनी मोर क्वेश्चंस?
Sir, do we solve some more problems on Stokes and divergence, or are these enough, sir?
No, this will be enough. I'm using the Stokes theorem and divergence theorem later anyhow. These are in the indirect way, we'll later going to use them very extensively.
Okay.
Kushal, hope I have answered your question. Any more questions? Okay, then I'll going to close the session. Okay then, good night. We'll continue tomorrow, beta. Take care.